Let's talk about atomic spectra and the Bohr model of the atom. We won't go into this in a huge amount of detail because it's not the current model, but we'll spend a little bit of time on it. We're not going to draw a whole bunch of orbits with dots in them because that's not really accurate. But we want to talk about what we can pull out of it and how it helped generate the more current model of the atom. So an emission spectrum is formed by an electric current passing through a gas in a vacuum tube at very low pressure. And that causes it to emit light. That light is a very specific wavelengths. So if you take our sort of graphic here, we've got a bulb, it's going to emit light, it's going to pass through a slit, making sure it's going all in one direction. Then it is going to split into different lines, and those lines are, in this case, of hydrogen. There's a red one, there's one that's sort of teal, and then two purple lines. Those would be characteristic of that particular element and sort of use it as sort of an atomic fingerprint, because a different atom will have different lines. And it's based on the electronic structure of the atom, and it's unique for each atom, so we can actually use that because we use the fact that electrons take on certain energies to make this happen. Here are some bright line spectra of some other elements, and then compared to hydrogen, you can see they're different. And so if I gave you a multiple choice here and said, hey, which one's hydrogen? Here's hydrogen for reference. You could pick it out of a lineup for sure. So that shouldn't be an issue, but you can see each element has a unique line spectra, and we can use that for identification purposes. Now, there's several different types of spectra you can take. You can get a continuous spectrum, like, for example, if you just run white light through a prism, you're just going to get a rainbow. We call that a continuous spectrum. There's no breaks in there, nothing like that. Now, if we take a hot gas, like in the example of our bulb apparatus, run a lot of electric current or hit it with a lot of heat, it will emit light, which we can use the prism to separate those bands, and we get an emission spectrum where most of the spectrum is dark, but we see lines at certain wavelengths. Now, if we kind of reverse that and run white light through a cold gas and run that through the prism, we'll see more or less a continuous spectrum, but the lines you saw in the emission spectrum are now missing in the absorption spectrum. And we can use that unique spectrum to identify spectra and elements. We can use it in the lab, we can use it for stars. That's how we know what elements are in the sun, for example, right? Nobody's actually gone and taken a sample, right? It's too hot. But we look at that absorption spectrum, we see what lines are missing, and then we can tell that that's characteristic of certain elements. But these atomic and molecular spectra are important indicators. Fireworks work on that same principle. And here's a picture I took one 4th of July, and you can see several different colors. Each color is characteristic of a different element. Now, Niels Bohr kind of built on Planck's idea of quantum theory. Planck decided that the energy had to be quantized. That means the electrons had certain values to their energies, and so did photons, for that matter. So Bohr said that every atom is going to have a discrete number of energy levels or orbits in which the electron may exist without emitting or absorbing electromagnetic radiation. As the orbital radius increases, then the energy of that increases as well. So Bohr used a value called with lowercase n, where n is equal to 1, 2, 3, 4, 5, so on and so forth. And those he called stationary states, and the electron, by being in one of those orbits that he numbered, would have a certain energy. An electron can move from one orbit to another by absorbing or emitting radiation or light of a particular wavelength, frequency, and energy. In the Bohr model, the electrons moved in circular orbits around the nucleus, where the motion is governed by the ordinary laws of physics, with the exception that the energy is quantized, that it takes on a particular energy for a particular orbit. So light of a characteristic wavelength or frequency is emitted when the light goes from a higher end to a lower end. So that's where the emission spectra comes from. Light of a characteristic and wavelength is absorbed when an electron goes from a lower E to a higher E. So that's the absorption spectra. I'll post a video link with some emission and absorption spectra and how the electron moves in that as an attachment to this presentation. In short, if we kind of look at this sketch of the Bohr model, you can see the orbits n equals 1, n equals 2, n equals 3. Then if that electron in green there goes from 2 to 1, it's going to emit light of a particular energy, a particular frequency, a particular wavelength. And so we kind of picture it as concentric circles like that, and they call it the planetary model of the atom because we say the electrons go around the nucleus like planets orbit the sun. You can also draw it in a little bit more straightforward way where you can see different regions of the spectrum. All those in purple are going from a higher end down to 1. Those are going to emit light in the ultraviolet. Those in green going from a higher end down to 2 are transitions that will be visible. So each one of those lines corresponds to one of the 4 visible lines in the hydrogen spectrum. The higher energy ones, the 6 and the 5 would be your 2 purple lines. Your teal line would be this 4 to 2, and that red line would be this 3 to 2, for example. So this would be 4 hydrogen. Bohr model really only works for hydrogen, which is why we don't really consider it for much going forward. But it does introduce the idea of quantized energy rather efficiently. From a higher end to 3, all those are infrared. And so the red lines are infrared, the green lines are visible, and the purple lines are ultraviolet. And so NL equaled 1 is ultraviolet, NL equals 2 is visible, and NL equals 3 is infrared. So when you do this in lab, we usually focus on the visible ones. So we focus in on that lower end of 2 for the lab. Bohr's theory does work well for hydrogen because we have a nucleus, we got 1 electron. It's got to be in some spherical region around the nucleus, and so Bohr's model works, but it doesn't account for things like electron-electron repulsion, therefore fails once you go up to, say, helium, for example. And so it's not an adequate model, and that'll actually push us into talking about a little bit more sophisticated model of the atom. Now, Rydberg comes along, and for the Bohr model of the atom, you can calculate the wavelengths of the lines in the hydrogen spectrum for the Bohr model of the atom, where 1 over lambda is equal to an R constant times the quantity 1 over the lower n squared minus 1 over the higher n squared. We do low minus high. That way you always get a positive number for your wavelength. If you're calculating wavelength, then the R constant is 1.097 times 10 to the positive 7th meters to the minus 1. Now, there are frequency and energy versions of this equation, but in the lab, a lot of times you talk about wavelengths, so we're going to work with the wavelength version of this equation. If you need energy or frequency, you can use the equations we've already outlined to get those without memorizing 2 more equations. And so I'll just let you do it that way because it'll be a little easier. So let's work an example. So we'll take that 4 to 2 in the hydrogen spectrum, and we'll calculate the wavelength of light from that. So if we look at this problem, we use our Rydberg equation, which I just copied it over, and then we're going from 4 and 2, and that's our R constant. That's just a constant. You'll use that same constant every time. So we're going to plug and chug and say 1.097 times 10 to the 7th meters to the minus 1 power. And then we're going to have 1 over 2 squared, that's the lower end, minus 1 over 4 squared, that's the other end. We run through the math, and we're going to get 1 over lambda is 2.06 times 10 to the 6th meters to the minus 1. That's not where we want to leave our answer, and it's a common mistake to leave it there because that's 1 over lambda. That's not lambda. So lambda is going to be 1 divided by that. So we need to take the reciprocal of 2.06 times 10 to the 6 meters to the minus 1, and we'll get 4.86 times 10 to the negative 7th meters. Now, a lot of times wavelengths of light are in nanometers, so if you multiply by that by 10 to the 9th power, we'll get 486 nanometers. And that's that teal line in your hydrogen spectrum. Now, in 1925, Louis de Broglie comes along, publishes his PhD dissertation, in that he assumed that electrons, which are definitely particles and not light, had wave-like properties. And he proposed this relationship, the wavelength is equal to Planck's constant divided by the mass and the velocity, where h is still Planck's constant, m is mass in kilograms, and v is the velocity in meters per second. Problem was is he didn't really give a whole lot of experimental evidence for that, so it wasn't terribly well received. But it turns out the premise was verified by Davidson and Germer within 2 years. Consequently, we know that electrons, and in fact all particles, have both a particle and a wave character. And it's a fundamental property of these submicroscopic particles. Once you get to something large, you work with normal physics. You're going to have to deal with quantum mechanics as the particle gets smaller. The experimental evidence was the result of these X-rays compared to electrons passing through aluminum foil. And it shows that the electrons had about the same wavelength as the wavelength in an X-ray. You see a little bit more of a blob in the middle for an electron because it's a bigger particle, but hey, those diffraction patterns look pretty similar, indicating that the electron definitely does have wave properties. To prove that to ourselves, we calculate the de Broglie wavelength of an electron. Electron has a mass of 9.11 times 10 to the minus 31st kilograms and has a velocity of 5.65 times 10 to the 7th meters per second. And we'll compare that to a baseball weighing 149 grams with a speed of 100 miles per hour or 44.7 meters per second. So compare that. Why is the difference meaningful? One's a really small particle that should have quantum properties, and the other one's a large particle or a baseball. We can see and touch that, where it's hard to say, oh, here's this electron. So there's going to be a distinct difference between the two when we do the calculations. All right, so if we look at this problem, I've pulled over the data for both. I've converted that 149 grams to 0.149 kilograms because I have to use kilograms to make the units work out. And the reason is if I look at Planck's constant, it's 6.626 times 10 to the minus 34th joules times seconds. But the units aren't going to seemingly cancel out unless you split the unit up. A joule is a newton times a meter, and a newton is a kilogram meter per second squared. But all that to say that the unit actually splits up and looks like this. And I'm going to split it up like this so you can see the units cancel. I can work the unit analysis for you another time if you really want, but we're going to go ahead and use these units so you can see them cancel explicitly. 6.626 times 10 to the negative 34th kilograms meters squared per second divided by the mass, 9.11 times 10 to the negative 31 kilograms times 5.65 times 10 to the 7th meters per second. You run all that through your calculator, you get 1.29 times 10 to the negative 11th meters for the wavelength. Now, if you remember, we said that the diameter of an atom is 1 to 5 angstroms, where an angstrom is 10 to the negative 10th meter. So this is on the order of 1/10 the size of the whole atom for a very teeny tiny particle that's much smaller than that. So what we can say from that is that the particle properties are there, but the wave properties are going to dominate in this case. So that would be our answer to part A. So then part B, do it for a large particle that should not have apparent wave properties. 0.626 times 10 to the negative 34 kilograms meters squared per second. And we're going to divide through now by that 0.149 kilograms and 44.7 meters per second. And you run that through, you're going to get something very small. 9.95 times 10 to the negative 35th meters. So that would be your answer for part B. So now comparing the two for part C, you can see that the wavelength for the baseball is much smaller than it was for the electron, but the ball was much bigger. So what we can say is that you're going to readily see wave properties for a small particle like an electron, but you're really not going to see them because that's much smaller than the size of the object. You would never see that. If I could make that work for a baseball, I'd be pitching Major League Baseball and not teaching chemistry. I could make tons of money, right? So we can see those wave properties are not apparent for the baseball, but are prevalent for the electron.